Okay, so before we begin, please confirm that you can hear me and see the slides clearly by just typing yes in the chat window. Also, we would like you to introduce yourself, your name, designation, company, and the country you are based in. I'm seeing replies in the chat box, and thank you so much. It's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. Great. And thanks for confirming. I would like to thank you all for registering and taking time out on a Sunday to learn about AIV, FIV approach and case study presentation in accordance with Energy Institute guidelines. My name is Aisha Khalik and I will be your introductory speaker for today. It's a pleasure to host this webinar for you. As a record, this is our 94th webinar in a series of technical webinars that we are conducting. As a practice, we are conducting one webinar every month. So please follow us on LinkedIn and YouTube and make sure to check our website for the latest updates. Today we have an experienced panel of speakers. I am with my colleague, Mr. Ijazul Karim Rao, Managing Director, Principal Integrity and Safety Consultant, Madam Mubina Khatoon, she is Director, Engineering Services, and Mr. Tony Williams, General Manager, Global Sales. Moving forward, during this webinar, we encourage you to keep asking questions to clear your doubts. We would definitely like your engagement on the topic. You can type your query in the question and answer window and you will receive a reply in the same window. Or we can answer your question live. We will try to answer as many questions as possible during this session. However, due to a lot of questions received in every webinar, we apologize in advance if your question is skipped. Before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of ourselves and those around us. Since this is a quite technical subject, we will touch only the theoretical and key aspects of AIV, FIV approach and case study presentation in accordance with Energy Institute guidelines. In this limited time of 2 hours, we request you to follow along with us and keep asking questions to help us make this session as engaging as possible. I'll start with Velosi introduction and tell you about what we do. Velosi is a leading global consultancy firm that provides asset integrity, management, HSE, engineering, environmental, and software solutions to the clients in oil and gas, energy, power, and petrochemical industries around the world. We also have our in-house proprietary software, Whale Plant, which is an industry-leading SAP-certified complete asset integrity solution currently being used by oil and gas giants like ADNOC, Dragon Isle, Turnip, BSR, and many more. Founded in 1982 in Malaysia, Velosi Group was then acquired by Apple Spain in 2011. With above 43 years of experience, we have expanded our footprints in more than 86 countries and have completed more than 1,300 projects with 500 satisfied clients. By combining global coverage and local knowledge with our wide range of services, we can create tailored solutions to complex problems. Our range of interrelated services and integrated approach ensures that we can accommodate a wide range of projects. This slide shows our worldwide presence.
Assalamualaikum and good day everyone. We are back again with a new webinar, this time AIV and FIV. AIV is like acoustic induced vibration and FIV is flow-induced vibration. And both of these phenomena are related to piping systems, like due to basically high flow. If some vibration is caused, those comes under these two categories. One is related to acoustic energy, other one is related to flow or turbulence related vibrations. By definition, if we try to look at like what is acoustic induced vibration, basically it's referred to structural vibration in piping systems, which is basically excited by flow and then further enhanced by intense acoustic pressure. Locations where it can mostly occur, the pressure reduction stations or wherever the high pressure drops are taking place, like PSVs, blow down valves, pressure reducing valves or choke valves at the basically valves as well. So it may cause some high vibration, so high sound, and that sound may convert into high vibration and then may cause fatigue failure. Locations, if we see on the PNID or isometric, if you see here, these are the PSVs and the PSVs downstream lines. Like you can imagine at a PSV, a set pressure is, let's say, 100 bars, and that it is being released into the flare headers, which is basically at 1 bar. So pressure drop could be 100 bar all of a sudden, and that increased uh, volume due to reduction in pressure on the downstream side will increase the volume of gas on the downstream of piping section could be quite high, and that would have very high velocities, and those velocities will cause these kind of issues. So please, people who are raising question like hands, you can write your question in Q&A session like windows, and we will be answering those questions in 2 breaks. One is in the middle and one at the end. So coming back to the presentation, here you can see an isometric view where BSV's outlet lines or blow down outlet lines are being connected with the flare headers, and then at the end these lines are heading to the flare knockout drum and to the flare. Next, like another example is a blow down valve, like a BDV valve, what we call it. And BDV is also like a system is operating at normal, and if there's any emergency in the plant, then we have to release the inventory to the flare side. So at that time, all of a sudden, there would be a high pressure reduction taking place across the blow down valve. And this activity normally takes place within 15 to 30 minutes time, but it causes very high vibrations and acoustic impacts, which may cause fatigue failure. So in PSV side also, PSV is like these 2 activities normally, AIV related issues, those occurs once upon a time, because the PSV is a normal failure rate can easily be taken as a 1 per year maximum, and BDV is also the same as maybe once in a 6 months time. So altogether, these 2 scenarios will occur on the plant almost 20 times in the plant design life maximum. So the issues are lesser, but whenever it occurs, the situation gets worse, and there are scenarios where failures and fatigue failures did occur on the plants. For normal, like young engineers, like these are the few like pictures of the pressure reduction stations, like compressor recycle valve, blow down valve, restriction orifices, relief valves, choke valves, and pressure reducing valves. Everything okay? Yeah. So now there are causes which again, what I explained, it is in the slide format or the presentation format, like AIV occurs as per the EI guideline. EI guideline mean Energy Institute guidelines, like a high pressure drop across devices, high velocity gas flow regions, turbulent flow regions, then pipe geometry and thin walled piping, acoustic resonance may also be a cause, then poor piping support and restraints. So these 6 causes, like if we say one by one, the major one is the high pressure reduction. And basically phenomena is when pressure is being reduced from high pressure to low pressure, just like a gas equation or by Boyle's law or Boyle-Charles law. If pressure would reduce, volume will increase. If volume will increase, flow velocity will increase. If velocity increase more than like a resonance, like a certain velocity limit, or it goes acoustic limit, then it can cause more high fatigue-related failures, high vibration practically. Turbulent flow is the same when high velocity Reynolds number get across more than, let's say, 5,000, 6,000, 10,000, it will be causing more issues because the driving force is more than the basically stopping forces or resistance forces of the viscosity. Then pipe geometry and thin wall, like we need to have a certain thickness of the piping at the downstream of the piping sections, whether those are the flare headers or other lines. So here, one thing which is important, AIV is a phenomena for the mainly for the flare headers or the low, wherever relief system is designed and built. Acoustic resonance, basically this is when the generated sound wave match the natural frequency of the pipe, resonance occurs, amplifying vibration forces. Then Other thing, if the pipes are not properly supported, guided, anchored, either with the stiff supports or medium stiff supports or medium supports or flexible supports, guides like anchors with the various kind of supports which are required to be placed on the piping, and then proper stress analysis is done to make sure the pipeline is properly designed and enough flexibility is provided to the pipeline in accordance with ASME 31.3 item 327, where flexibility criteria is there. If that is defined, then pipes will work properly, otherwise it's one of the costs. Then others are the mitigation measures, how we can avoid AIV related issues. Then the first thing is reduction in the mass flow rate. If we can change it, it's a redesign. If we have a certain equipment and we have a certain volume of fluid inside the inventory, so it cannot be practically reduced. So the desire is, it means you may have to make 1 train, 2 trains, 3 trains. So as whenever we need to evacuate or release any volume from any particular inventory, that quantity is not that high. So this is the one of the criteria where we can basically reduce AIV chances by reducing the mass flow. Change of the valve trim. If there are pressure reducing valves, there are various kinds of trims are there which produce various levels of the sound. So the low level trims would be costly, high sound trims would be cheaper. So it means the cost benefit analysis or design complications. So one of the recommended solution is the valve trim should be able to produce lesser sound, or it could be a multi-stage kind of valve, so which can help to reduce the basically pressure reduction, not from sudden, it could be at various levels. Then the downstream of the control valves or pressure reduction valves, what length could be provided, though it is basically limited by the space available on the pipe rack and how far is the subsequent header of the flare. However, if could be extended, then every 50 basically diameter 3 dB sound could be reduced. So the state pipe, then it can help to reduce the AIV threat. Then change in wall thickness, to reduce the chances of the fatigue failure, sometime we have to increase the thickness of the flare header or basically flow header, and that is also a cost, and there is a resistance from the a TPC stage, but this is one of the potential solution. Then removal of circumferential discontinuities. If there are small bore connection, any unnecessary small bore connection should be avoided, because these small bore connections are one of the potential failure location, or there could be a connection as a small bore as an injection point. That is also a potential threat for the fatigue failure. Now, other part is also there, if these small connections are there, whether they are made as a weldolet or swipelet. So a swipelet can help to reduce basically the failure rate, and number of take cycle could be extended. Then use of circumferential stiffness ring. This is we have stiffening rings in the pressure vessel against external pressures. 4 or 5 angles are welded with the vessel, same as those stiffening rings could be welded with the piping headers, and it will also help to reduce the fatigue failure threats. Now, if we go to next is FIV, both are side by side, but it is a flow related. If high velocity, FIV is the result of a turbulence in the process fluid, which occurs due to major flow discontinuities such as bends, tees, and partially closed valves and small bore connections. FIV is typically on centrifugal compressor piping system. Some risks may also exist with high flow screw compressors. FIV is also a problem on production risers, heat exchanger tubes, and many other industrial applications. So location-wise, it's a PNID, same. All the when we try to define excitation sources for the AIV, it is very simple. For AIV, it is downstream of the blow-down valves or PSVs. Whereas for FIV, all the pumps, compressors, or the dead legs, T-joints are the potential locations where FIV-related failures or a threat could be there. This is another example of FIV in the PNID form. Then the main causes like is a turbulence in the flow, like high velocity flow create irregular pressure fluctuations leading to vibrations common in long straight pipes, especially with high gas flow rates. Then vortex shedding, like wherever, for example, if a nozzle is connected with a piping system or the T-joint, if there would not be a vortex breaker, it can have some vortex, and that vortices can create some sort of basically FIV related issues. Then flow separation, abrupt change in pipe geometry, for example, reducers, elbows, and dead legs lead to flow detachment, causing unstable pressure zones. Then pulsation, like induced vibration, for example, piping at the downstream of the, let's say, positive displacement pumps like piston-driven pumps or compressors, then it may have a pulsation-related vibrations, and that may also cause FIV-related threats. Then dead leg and branch connection, as I said, T-joints where vortex or vortices can come. There is also, or if lack of supported, that could be a problem. And same as unsupported piping sections, if vibration and the vibration is further increased by resonance of the vibration, it could be excited by the like a source equipment, maybe from the pump or compressor or from the valve, that may also cause issues. And if pipe is not properly supported or anchored, it may also have a high vibration and can cause FIV related threats. So if you see one example shown in this picture where T-joint is there, and in this T-joint, if you see if a connection or injection is coming from a branch to a main line, how kinetic energy could be basically created, and that can cause FIV related. So in this way, the vortex breakers are required to be installed, and proper thickness is required to be provided to avoid this FIV threat. Now, another example, like where the same issue is like how this T-joint and diameter of the vertices, how it could be basically stopped or prevented. One example is shown here. The typical solution to FIV problems are listed, like change the length of the dead leg, typically shorten, avoid certain flow rates of the gas, which practically not possible because equipment or system is designed for that reasons. But if there's any alternative mean that could be looked at, then allow some flow through the dead leg, typically a temporary solution, while permanent solution are developed and installed. Add spoilers to the mouth of the dead leg to eliminate the creation of vortices. Add additional support and bracing to reduce the vibrations. So these are the few issues. I will be discussing it further, but it is an initial like discussion or initial like taking you people along. Then if we say AIV, FIV cause potential failure locations, if we see, mostly these are the T's, bends, right, small bore connections. Then welded pipe support such as pipe, shoes, and anchor may also be impacted. So here, these are the main three locations. But we see like T, branch connections, small bore connections, such as the vent drains, instruments, and sample connections, then welded pipes. So identification of valves or valve group which generate sufficient noise energy to be potentially acoustic fatigue concern. Identification and evaluation of the appropriate noise and vibration control measures to reduce the risk of AIV or FIV to an acceptable level. So these are the like major potential locations. Here, if we see how it look like, there's a one example where piping fatigue has caused a crack on the T-joint here. The vibration of pipe work cause dynamic stresses, which if above the critical level can result in the initiation and or propagation of the fatigue crack. Another example, here fretting. For example, if the two surfaces are there where pipe is being supported by another metal, and if there would be a vibration, there could be a potential corrosion on both the surfaces. So this is one area where vibration combined with thermal movement can cause a major fretting threat. Here, if like a vibration and then joined with a bigger pipe, this joint is, if you can see example, being affected. So this kind of failure can also occur. Now, FIV, like how we can reduce, like again, discussion is the same, increase the diameter of the main pipeline if it's possible, if it's a new design, or if we are having a problem, it means a modification in the plant. Running a second pipe in parallel to having a like two trains, we can say, changing the operating condition if possible, which is practically not possible. In general, a plant is already built. Then flow smoothing. Flow smoothing can be accomplished through the use of swept tees rather than 90-degree tees, minimizing the number of bends in the system. Then like a pipework support that could be further like some repetition is being presented, but it is like, if you can remember, like what are the mitigation measure, what are possible solution. The pipework supports composite pipe wraps and change in section like a wall thicknesses. Here, how we do AIV, the methodology point of view. So Energy Institute section T 2.7.3 that provide the complete methodology like how AIV assessment can be done. So Mr. Rahil Afzal, you can add your questions in your Q&A session, because I cannot take your question. You are raising the hand, just I'm informing you. So we'll be taking questions in the break as we will completing certain section of the presentation. So here, the first thing what we do, data collection, data mapping, data validation, identification of vibration excitation sources. Then PWL is a power level calculation for the basically sound in accordance with the T 2.7.3. Then LOF calculations as per the EI guideline of section same, and then mitigation measures to reduce the AIV threat. Similarly, for FIV, same kind of data mapping, data collection, data validation, identification vibration excitations. Then here we are calculating basically EI guideline T 2.2.3. And here we try to do by kinetic energy calculation, and in the AIV we calculated by power sound power level calculations. There is a scale on both sides. The ultimate effect is fatigue and crack, but their causes and their calculations ways are different. One is driven by like kinetic energy driven, which FIV, and sound power level is for the AIV calculations. Scale point of view, there, like we'll see in more detail. This is an initial like introduction point of view. If LOF is less than 0.3, it is not a problem. Like between 0.5 and 0.3 is still acceptable, and here the equipment which are coming under small bore connection, which would be a potential threat, which may cause like some problem for them. Then if LOF is between 0.5 and 1, then main pipe as well as small bore both are required to be given due attention. Greater than 1, some kind of corrective action is required. Whether change in the design, additional support, additional thickness, a reduction in the flow, any mitigation measure is required to reduce the LOF less than or equal to 1. So now, like if we have to do the job, how we can do it? There are international standards which can be used easily. So first standard is Energy Institute guideline. So it got various sections, like a guideline for the avoidance of the vibration-induced fatigue failure in process pipe work. That is the title of the standard. It got various sections like introduction, overview of the piping vibrations, undertaking of the proactive assessment, troubleshooting of vibration issues, technical modules, inspection of buried piping, then change to the approach from MTD guidelines, sample parameters, SBC LOF assessment guidance, worked examples, and other terms. So this is like some index I'm not going through. Anyway, we can say spend little bit time here. So same thing here, introduction, overview of the piping vibration, undertaking of the proactive assessment, troubleshooting a vibration issue, basically, and then technical modules are there, whether qualitative, quantitative, all, then various appendices are there. Then another standard, which is API 14E, recommended practice for design and installation of offshore production platform piping systems. For FIV, it is very important to follow API 14E criteria. If we will be following API 14E criteria, then any system which would have been designed in accordance with API 14E criteria will meet certainly the criteria of EI guidelines as well. So here, section 1, general, then piping design, selection of valves, like then fittings and flanges, design consideration for particular piping systems, then consideration of related items, installation and quality control, example problems, and so on. Same way its index is there, it's a big index, but it's a very common industry standard to design hydraulic sizing of the piping systems of the upstream facilities basically. Then there is a PSV's sizing standard, which is ABI 520. It got sizing and selection, and the two parts are there. So it is also important standard when it comes to the sizing and selection of the PSVs or PRVs. PSVs in process safety valves. It is the index for that standard. Then API 521, which is pressure relieving and depressurization system. This is also another important standard for the design of the relief system and flare headers. So it got various systems and various sections like introduction, cause of overpressure, determination of individual relieving rates, selection of disposal items, systems, disposable systems, the determination of fire relief requirement, special system design considerations, and so on. This is the index of API 521. Then inspection of the PSVs. If we wish to refer, API 576 is a good guideline for the inspection of the pressure relief devices, the frequencies and type of inspections. This is the index of API 576. Then there are some best industrial practices as well, like Saudi Aramco has issued a standard SAS L310. Also the other subsequent standard which are related to fatigue and vibration control as well. Those standards could be referred. So this is one example. Then this is the basically SES index, like a vibration consideration is also one of the activity in that particular standard. Here is the ad hoc standard which AGS PH 08-002 content. So which like a flare and blow down philosophy. Under that standard, there is also vibration fatigue criteria which should be followed. So all the organizations almost they are familiar about this threat, and it is a one part and parcel of any piping system design activity. Then there is also another standard coming from the Shell side also. So Shell also basically study basis content for the AIV study basis. So we are also giving a reference. So Shell is also having its own standard. So three best industrial practices coming from the three operating companies. Then there is also in top of EI guidelines, there is the one equation which is very famous, which is Nishiguchi equation, or Asinger curve is also called. So where alternative fatigue life, number of cycles, and could be calculated, and the maximum power level, sound power level, which is the capacity of the thickness of the pipe, could also be associated. So Nishiguchi equation and the EI guideline works hand in hand. So they supplement basically or complement each other. So these are the standards. So now basically if we go through the case study, first we'll cover one case study of AIV, then we'll go to FIV. After AIV, like as this first case study will complete, we'll do the question answers, and then we'll go to the FIV case study, and then the mitigation measures, and after that we'll have another question answer sessions, and then we will conclude the discussion. We know that the month of Ramadan in the Muslim areas, so but anyway work goes on, and we are trying to share the knowledge as we can. So project objective, like a case study means that we have done a practical work for one of the project. We have basically changed the data. We have also mixed various case studies, so as any one result is not shared with anyone. So if you find some kind of conflicting information that may come from two different projects, but concept wise, we have tried to present all the set of the basically steps. So here assess the piping and piping component of the system for areas of potential concern related to AIV and FIV. Record the AIV FIV screening result based on EI energy dispute guidelines for the avoidance of vibration induced fatigue failures, and the countermeasures for avoidance of piping fatigue failure due to AIV and FIV both. So here scope was like a Velosi process department to identify the AIV, FIV prone lines and shall carry out the analysis and recommendations. Identify and confirm the lines that are likely to fail due to AIV and FIV and carry out a detailed fatigue analysis on the specific lines identified that warrant it. Then recommend measures and mitigation of the fatigue failure due to acoustic for the identified system. The number of PNIDs were 169 and the AIV related lines are 133 and FIV related lines are 408 what we studied under this project. Here, what are the deliverables? Number one, a detailed AIV study report, which is basically the last one. Then here identified lines marked on the PNIDs, isometric drawing with the required recommendations, a detailed calculation sheet, a calculation validation sheet, and a detailed study report, which is basically the first one. I mean, 5 deliverables are there as a part of the report. Then how we do it? They like the same steps what we discussed in the earlier, but like here we have also added the Nishiguchi aspects. Like first thing is always data collection and data mapping. What is available, what is not available. Then identification of vibration excitation sources on the PNIDs, basically also the isometric drawing we mark. Then preparation of line list populated with required engineering data. Then level 1 PWL, like a power level for the sound calculation as per the EI guideline T2.7.3. Then we are also calculating the PWL by Nishiguchi equation, like what the maximum one. This is actual PWL which is generated by the pressure drop across the valve, and then what is the capacity of that piping system which can take as per the basically D over T ratio, diameter over thickness ratio. Then calculate equivalent thickness for the LOF side by the Nishiguchi, and then also we see what is acceptable by the system. Then calculate number of cycles of the failure and using power PWL sources. Just a minute, this is the last step. Then we calculate the fatigue life of the particular piping system under that situation. Here, as a step, the same thing, reflection of the PNIDs, BFDs, isometric drawings, then identification of acoustic sources, calculation of PWL, and then correspondence, same calculation by the Nishiguchi equation, and then segregation of the piping system for the PWL and LOF calculations. Then we see that which one is coming at the acceptable level of 0.29 factor, where LF is 1 or greater than 1 or less than 1. So those are calculations are done. Let me go to next stage. Like what information normally we collect? Line list, PFDs, heat and material balance data, the specification of piping material, piping support standard, resolution specifications, PNIDs, isometric drawings, PSVs data. Then normal process data, what we need is fluid density, mass and volumetric flow rate, then upstream and downstream pressures, molecular weight of gas, temperature, fluid phase, viscosity, and piping specification. So here one thing to remember, the AIV is basically applicable for the gas lines only. It's not applicable mostly on the liquid side, because in liquid side that kind of flow, like a change of volume, is not practically possible. Then what is the first step? Identification of vibration excitation sources. It is done both for the AIV and FIV. So here, like we gave example previously, same example is repeated as a part of the case study, and we have marked the excitation sources with coloring and cloud. So here, leaf valve, blow down valves, restriction orifices, pressure reducing valves, compressor recycle valves, and choke valves are identified. Another example, PSVs and blow down valves are shown here, right. Now, step 3, preparation of the line list populated with required engineering data. So this is like all the lines where we have the line number, PNID number, line size, molecular weight, upstream set pressure, downstream pressure, upstream temperature, mass flow rate, and here we have also built in the formulas for PWL calculations, LOF calculations, and so on. So this way the complete worksheet is prepared. Then here, what kind of data is being used? For example, upstream temperature, pressure upstream of the pressure reducing device, pressure downstream of the pressure reducing device, molecular weight of the gas, mass flow rate, external diameter of the main pipeline, internal diameter of the main line, external diameter of the branch, distance between source and the welded discontinuity, the next bend or a small bore connection, then wall thickness. So all these values are required to be filled in the template to calculate the PWL as per the formula. So now calculation as per the EI guideline. So I showed you earlier also, the formula is built in the previous sheet here. This is the formula. It is going to the step 3. So same formula is shown here. PWL is equal to, main is the upstream pressure minus downstream pressure. Next, the molecular weight, temperature, and so on. So here, if PWL is less than 155, it is not a problem. But if it is greater than 155, it is a problematic, and it required to be reassessed, and it has to be seen if we have to have some mitigation or some extra margin is available in the piping system thickness and design. So now this is the EIL guideline table from that 2.7.3. If we try to see it here, what we do, normal formula. Then if the source value is low, noise stream fitted, like low mean yes, then the PWL reduced to account for effect of low noise stream, refer to note 1. For example, is the PWL greater than or equal to 155? This one. Greater than, yes. If no, it means main line LOF is equal to 0.29. So if 155 dB, no problem, less than or equal to. If more than, we have to be first worried about the small bore connection. Go to next welded discontinuity, for example, SBC, welded T, welded sport. Then calculate the PWL in the main line, add the discontinuity, accounting for attenuation, PWL discontinuity is equal to PWL like a source minus 60 L over D. Are there any individual source that has to be added? Relocate PWL at the discontinuity, considering those factors, it has to be done. Then is power PWL greater than or equal to 155 dB? No, main line is equal to, line LOF is equal to the greatest discontinuity location LOF up to this location from the source. Subsequent length of the line has an LOF equal to 0.29. Otherwise, we have to go, yes, calculate the LOF of discontinuity, refer to flow chart, means next level we have to go. So this way, like one is simple calculation, other is attenuation or discontinuity. Those factors are accounted for, thickness is accounted for, and then accordingly we see that if we can stop there, we have to go next stage. So same steps are explained here in the next 7 slides. For example, the formula to be used is same, which we explained earlier. So this is the values of their used, and it has to be dimensional consistency, like all the units what we are using, they should be in the same format, needless to say. Then PWL state is coming, where like C value is there, PWL Nishiguchi equation also is used, right? Like first by EI equation, which is 176 dB, and the second one is by Nishiguchi equation, which is taking the extent of the thickness available in the pipeline. So it is giving 180 dB, little higher than what is calculated by the P1 minus P2 formula. And this is a Singer curve. If like a ratio wise, pipe to dia to thickness ratio, if we calculate that, and if that thickness comes here, so then we can see what is the allowable PWL for that particular pipe. If actual PWL is less than this ratio, then there is no problem for the piping system. If the actual PWL is greater than the required as per this curve, then there is a corrective action required. So Nishiguchi equation and the Singer curve, both are basically side by side. One is a graphical form, other one is equation. Which equation? This equation, like minus 20 log d external over T2 plus C. This is the Nishiguchi equation. Sorry for like the way I'm pronouncing. Next is this the same shown on the graph, and then as a result we have identified 133 pipeline where 129 matched, they are below 155 dB ratio, and the 4 were above basically 155. All the calculations are further calculations required to be done for these 4 lines. So this is the like a result. You can see that PWL value with the lines wise where data was gone. This was a set of the lines, but you can see more lines here, more than 155, but these are the various strains of the same system. Then calculate equivalent thickness which provide LOF1. So here we have used basically the flow chart show that methodology of LOF calculation as per EI guidelines with Nishiguchi equation, like you can use PWL which is 175 or you can use 180 and the thickness formula, and with that combination like the number of cycles with Weldolette kind of small bore connections or Swipelet kind of small bore connections, because with Swipelet we can get the extra number of cycles with a factor of 2.57 extra times as compared to the Weldolette. It means Swipelet is a better design as compared to a Weldolette kind of small bore connection. So here what we are achieving here, for example, from the previous section we came here using PWL at the location of interest, then this is the equation with the number of cycles are calculated by the formula. Then if d over dt is like greater than less than 10, then this equation, otherwise this equation, then accordingly we will be getting LOF if it comes like a less than or equal to 0.5 or 0.29, which is ideal, the ideal condition. Then step 4, the flow chart, like the same calculation, the number of n is calculated with beta factor S, A are calculated. Then here the beta calculation is formulated. Then here the number of like n is like 1,000, like it's coming as in million. So number of cycles which could be like sustained by these piping systems are calculated this way, and then accordingly LF is calculated by the formula given, and LOF is coming 1, or LF is coming also 1. Here we have calculated all the number of cycles which could be like sustained by each piping system. So then we have to see what would be the actual number of cycles, and these number of cycles ratio wise whether we will have enough fatigue life. Next step, calculate the number of cycles to a failure and LF using a PWL source, right? It is the same equation. So the number of cycles again by using basically EI guidelines. The first one was, if I go back, Nishiguchi equation. The number of cycles by this equation where we are using the maximum extent. Other formula we are using the EI guidelines, and then accordingly these number of cycles are more than the Nishiguchi. Okay. Then we have now the lines which are LOF coming 0.3130 from 0.5 to 0.30, and then 1 to 0.5 number 3 line, and greater than 1 is 0, none. So this is the number of cycles by the EI equation. Now calculate the fatigue life. This is one area where when we say fatigue life means the how many cycles these practically would be there throughout the each event, and then what would be the maximum extent of that particular system to sustain. So next we evaluate the fatigue life by effective frequency defined by the following equation. This is the equation coming from basically Nishiguchi and site, and here the number of hertz are coming. This is the equation, or which is calculated as 1629. Normally we take as 1600 hertz is a normal frequency for each event for the comparison purpose, and actually can be calculated by this equation if the line dies between 100 mm to 1000 mm. So here therefore the basically F effectiveness is 1629.77 hertz Then the fatigue life basically is covered N, which is coming from previous two calculations, divided by F effectiveness is 1600, divided by 36 is a conversion factor. So here 16,000, this divided by 36. So the fatigue life is coming 28.63 hours for this particular piping system, which is being presented as an example. It is assumed like now what is the operating life of the basically BDVs or the PSVs. As I said earlier, if we assume these systems would be operating, let's say 20 times in a operating life, and every time the operation time would be maximum 30 minutes, so then it will be coming 10 hours operating time. If we take 20% extra margin, then 12 hours is taken as an normal operating life of these PSVs and blow down valves. Remember, we are not talking about normal operation, we're talking about the two type of valves which are used to release the fluid in case of any abnormal situation on the plant. So this way we have calculated the basically fatigue life here 4 hours for each event. This is for each hour, for each event basically. Now, what is the recommendation and the finding and recommendation? So we found that the PSV's downstream line, there was a requirement of increase in the thickness from 9.5 to 12.7 mm. And for blow down valve, thickness is already quite high, and it is recommended to change the trim of the basically the BDV valves here. The multi-hole, multi-stage type low noise trim valve should be selected to mitigate AIV risk as per Fisher Emerson valve specification. Up to 11.2 dB sound reduction can be achieved. A swipelet to be used for the ATM vent connections instead of weldolet, since FLM for swipelet is 2.7 time, which is higher than FLM of weldolet, which is 0.5. Now, discharge header thickness is required to be increased from 9.5 mm to 12.7 mm up to main header. This increase in thickness is recommended to reduce LOF value from 1.1 to 1. Swipelet to be used for ATM vent connection instead of weldolet, since FLM of swipelet is 2.7, which is higher than FLM. So this is the recommendation, and then we prepared the report and submit it. So before we go to the case study of FIV, so we will take the question answer break now. So Mr. Ali, and then there will be last part of the presentation FIV, and then we'll take another question answer session at the end, and then we will conclude the discussion. I would also introduce my colleague, Mr. Mujtaba Talat. Basically, he's the working engineer on this job, and he basically prepared this presentation for me, and I am mainly presenting on his behalf. So he would also be helping us to answer the questions because he's a working engineer. Okay, and we'll also give chance to the people. You can introduce yourself and ask the question. Introduce your name, your organization, and your location, so as other people may know. We know that this topic is like a very specific topic on a technical aspect. Everybody is not relevant to AIV and FIV issues.
I can only understand it's applicable for full vacuum under external pressure, but now my doubts were clear.
Yeah, but there's a formula available for the LOF calculation under EI. If we take, for example, attenuation by the length and by weldolet to swipelet, and then if we add the stiffness ring, or we increase the thickness, all these options are there, and stiffener ring is one of the options to reduce that. Okay, sir. Next question. Thank you, sir. Ahmad Shahid.
Assalamu alaikum.
Walaikum salam.
Sir, I have two questions to ask. First of all, I want to ask that do you offer CPD point for Pakistan Engineering Council certification for attending this webinar? And my second question is that I am working in a pharmaceutical manufacturing company. So I want to ask that we have to transfer thick fluids like syrups or ointments for shorter distance. So for shorter distance, like 100 meters or 200 meters or 300 meters. We don't have such piping arrangements that we calculate all these things, but we just have piping according to the fluids, so that fluids can be flow in that pipe. So is it be beneficial that I'll apply these all analysis to calculate the piping design and to implement the new piping design? Will it be beneficial? I want to take this as a project and I want to work on this. I want some your guidance regarding all these calculations.
See, first question, like, yes, we are registered with the Pakistan Engineering Council, and if you will be attending this course, you will get the CPD point, and you can attach your certificate, what you will get after attendance of this course, and Engineering Council will accept that. Coming to the second part, like there is always a concept of reverse engineering. Both AIV, FIV basically generate vibrations, okay? And if you are facing any problem of vibration, high vibration on your piping systems, then you have to do the study. Otherwise, you don't need to worry about it. So if there's a high sound, which is AIV related, you can feel that on the plant. If there's high sound coming from the piping system. Secondly, you can do the vibration measurement of the piping system. If there is any kind of high vibration more than the threshold limit, then you have to see what the cause is. Causes could be fluid, cause could be lack of supports, or there could be lack of anchoring. Then accordingly, you have to take some corrective action. So it is not required to be to take any action if you don't have any anomaly or abnormality on the current plant operation. Okay, sir.
Okay, thank you.
Thank you, sir. Mrs. Sudhanshu, you are allowed to speak. Kindly, please ask your question. So, hello, sir. I am Sudhanshu, and Kashyap is working as a piping engineer. Question is from Noida, India, and is about to flow-induced excitation calculation, which lines are applicable for the study in gas line. See, mostly in the gas lines, at the pressure reduction stations, we assume AIV aspects, and other areas, whether it's a gas, whether it is a single phase, multi-phase liquid line, FIV related issues could be there, but we have to see the excitation sources. Then where the high velocity areas are there, then accordingly we can measure the vibration in the field, and if any corrective action required, that action can be taken. So other question, we completed the presentation now? Okay. So other question is, SDVs, shutdown valves or MOV valves are applicable or necessary to this AIV FIV study? C. Shutdown valves, MOV valves are the type of operation of the valves. We are talking about pressure reduction valves. These valves could be operated by any mechanism. They could be automated valves, or they could be operated by actuator or motor. So the issue is caused by the pressure reduction through those valves. Okay, sir. So type of the valve matters with the pressure reduction nature, not how the valve is being operated. So we now continue our discussion, presentation, last part FIV case study, and some mitigation measures are there. Then at the end of that session, we will come back again for the question answers. Please keep writing your question in Q&A session, and we will also give you a chance to speak, and you can ask your question directly. So case study for the FIV analysis, deliverables like a detailed FIV study report is basically at the last outcome. In between, we identify lines, we mark the lines on the PNIDs where potential FIV may take place, then isometric drawings with the required recommendations. A detailed calculation sheet would also be developed and shared, a calculation validation sheet, then a detailed study report is prepared. Here, like stepwise, we have 8 steps to follow for the FIV study. The first thing is like data collection. Once it is done, we go for identification of vibration excitation sources, then preparation of line list populated with required engineering data, then determining PV like SCARE as an EI guideline. It is basically kinetic energy calculations. Then determining a fluid viscosity factor.
I want to ask
you to unmute. As per EI guideline sections, right? Then determine support arrangement as per EI guideline section T 2.2.3. Then determine flow induced vibration, basically factors per EI guideline section T2.2.3. Then calculate flow-induced turbulence LOF as per the EI guideline on the same section. Then last is the mitigation measure to reduce the LOF. Then like how we do the same steps, we identify the list form, identification of excitation sources from the PNIDs, preparation of acid register along with all required input data, determining the kinetic energy calculations, determining the fluid viscosity factor, determining the support arrangement assessment, determining the flow-induced vibration factors, calculation of the likelihood of the failure, then identification of the mitigation measures. Here, like how we do it, like a kinetic energy calculation is done by the formula, and if it is less than or equal to 10,000 kg per meter second square, then it would be acceptable. Then next thing is like for liquid and multi-phase fluid, F is equal to 1 basically. For liquid and multi-phase fluid, FBF means viscosity, fluid viscosity factor is 1, but for others, gas and multi-phase fluids, we calculate by the equation FBF, which is given in the bottom. These guidelines are coming from EI guidelines from the Energy Institute. Here, if we see that, determine the support arrangement, if there are various kind of supports like a stiff, medium, and flexible. So there is a typical fundamental natural frequency, which our colleague asked earlier, whether is with flexible 1 Hz and stiff is coming 14 to 16 Hz natural frequency. And then in between there's a calculation distance span of the basically supports on the piping system. Then factor wise, as we calculate, there is a equation for the each type of the basically arrangement, and then there is equation. We need to have alpha factor, we need to have beta factor, and there is a basically formula for each. And then after calculation, we go to the LOF factor, which is this is a formula. And then if LOF is less than 0.3 or 0.29, it is acceptable. Then there's a range. LOF greater than or equal to 1, which is a high risk, which is between 1 to 0.5 is a medium, and 0.5 to 0.3 is a basically low, and LOF less than 0.3 is very low. And accordingly, based on the LOF factor, various kind of considerations are required. It means if LOF is greater than 1, we need to redesign or recheck the system. Similarly, for 1 to 0.5 also, the main line should be redesigned, re-supported, or detailed analysis of the pipeline should be conducted, or vibration monitoring of the main line should be undertaken. Corrective action should be examined and applied as necessary. Similarly, if it is LOF 0.3, then only visual inspection of the installation, no other action required. But if 0.5 to 0.3, like small bore connections are required to be given attention. So these are the like a scale 1, 2, 3, 4. There are 4 categories of FIV where actions are required to be taken accordingly. Then if it's small bore connections, then LOF factor, small bore connection like less than 2 inch and so. If a LOF factor is 0.7, still it is significant and redesign or correction is required. If it is between this, then SPC should be monitored with vibration measurement, and if a low potential for vibration induced fatigue like LOF is 0.4, this scale is for the small bore connections. FIV study assumptions, normally we assume that the bypass lines are basically the pressure is 1 bar at the opening, then main line valve will open after the pressure has been like equalized by the bypass valve. Similarly, for hydrocarbon liquid condensate valve opening, the vapor pressure is assumed to be equal to the upstream pressure. For liquid multi-phase closure, the upstream pipe length has been set to a default of 100 meter. Then this will be assumed to up to either one next major vessel or a change in pipe diameter, assuming a 2:1 ratio or more pipe diameter changes. So this was like a just summary, like how we do it. Now we are going to the examples like one by one. Identification of like a vibration excitation sources, we informed you earlier also. Like first we get the information, the same just like AIV, PNIDs are more important, isometric drawings are more important than the other data which is available. Then we mark the these location on pipe by pipe wherever we feel the excitation source is available. Somewhere you are not closing the mic of the attendants. After identification, step 2 is the preparation of the line list populated with required engineering data. So the same as we did in the AIV side, the line number, phase, viscosity, mass flow rate, density, diameter, outside diameter, wall thickness, maximum span length, area, velocity, and this is the kinetic energy calculation. Then the input data we normally take is the external pipe diameter, maximum span length between supports on the line of interest, wall thickness of the main pipe, fluid velocity, gas dynamic viscosity, fluid density, and all this data is basically used in the system sheet. Then, like how we calculate the kinetic energy calculations, which is PV square, the determine fluid viscosity factor first, then determine support arrangement as per the sections, then determine FV as per the section, the calculation flow induced turbulence LOF section T2.2.3.5. Then advanced screening method can be used, like advanced screening method fundamental natural frequency, which is 1 to 3 Hertz, section T2 to T2.2.4. Then flexible system with LOF greater than 1, where the actual natural frequency are known and between 1 to 3 Hertz, amend the LOF basically. Here, how we calculate this? PV square mean fluid density and fluid velocity, driving value from input parameters, and this is the number which is 18,146 is greater than 10,000 basically. Then here the scale wise, how we estimate, like as per the client requirement, they didn't use the scale of 10,000 kg per meter per second square, they used the scale of 5,000. So all the lines where basically the kinetic energy calculation is less than 5,000, those are 357, between 5,000 to 20,000 basically kg per meter per second square 47, and greater than 20,000 were 4. Total of 51 tags have kinetic energy greater than 5,000. This is the basically the kinetic energy formula results in the Excel spreadsheet, and all the formulas were built in the same Excel spreadsheet. Then determine fluid viscosity factor. This is just a formula, but here since the fluid is if the liquid, then it would be taken 1. So this is the factor which we have calculated based on the multi-phase flows based on their composition and data. Then determine support arrangement for the piping by piping. So here if you see that like a span length coming outside diameter with the stiff, medium or flexible. So mainly pipes are coming between medium stiff, and then we get the maximum span length of the piping supports. So here like one of the piping span is coming like 3.5, and the stiffness like this is the outside diameter is coming, let's say 60 mm here. Then the overall support arrangement wise, we divided all the piping system which were under study: stiff 4, medium stiff 327, medium 77, and flexible were 0. So this is the stiffness type. For each pipeline we have done the identification. Then next step is determine flow induced vibration factors as EI guideline section T2.2.3. Here like these are the first, when we come to determine the flow induced vibration factor FV. So we have to calculate, this is the formula, we have to calculate alpha and beta, which are calculated as example. These calculations are done for each pipeline basically, piping system. This end result is FV calculations, which is 40,470, and then this FV factor is calculated for each line in the Excel spreadsheet. So next, calculate flow induced turbulence LOF as per EI guidelines section T2.2.3. So this is the formula, which is flow induced turbulence LOF is 0.45 for one of the example line. So then next is decreasing maximum span length from 3.45 to 3.2 meter in order to change support arrangement from medium to stiff or to stiff basically. Determination flow induced vibration accordingly. So here the calculation point of view, alpha beta calculation, FB number calculations, and then we have the flow induced turbulence LOF is coming 0.29. By reducing the span of the piping system, piping support, LOF factor is reduced. In this way, LOF category wise, lines with less than 0.3 or 336, LOF between 0.5 to 0.32, LOF 1 to 0.52, and LOF greater than 1 or 8. Then Calculation of LOF, overall LOF result. So here we have shown the LOF result of all lines. Last, mitigation measures to reduce LOF if required. Here in this pipe, the pipe tag accessible to flow-induced vibration were assessed as per AIV pipeline. 12 piping tags have LF greater than 0.29. However, the intermittent operating lines for PSVs are acceptable with low risk. Therefore, no mitigation measure or no change was recommended. So this way, we completed FIV assessment steps. Now we are going to troubleshooting a vibration issue and good design practice. This was also one of the questions coming from our friend from the pharmaceutical industry. So here, review history and plant operation. Like, it is not like a plant is already working. At that stage, we are getting worried about AIV, FIV. So in that scenario, we need to identify location of the failure and any similar accessible locations if some failure occurred in past. Correlate operating condition with high vibration or failure history and identify under what condition the vibration occurs. Then review failure investigation and or metallurgical reports. Then review failure investigation and repeat it. Review previous design studies. Then accordingly we can make the decisions. So first, like, we can walk down. From the walk down of the plant, the following information is being sought: identifying where the pipework system is having high vibration. Consider excitation connected items, for example, SBCs, small bore connections, instruments or tubing. Note condition of support, for example, damage, loosening and ineffectiveness. Then a subject assessment of the type of vibration occurring. So here, for example, steady state, transient or random in nature, exhibit tonal properties. Then is the response subjectively low frequency or high frequency, or their impact type and the events. These are the examples when we try to find out the issues with the existing piping. Then information from the plant operators, like recording plant operators operating conditions is crucial to assess the vibration issues, as these conditions affect excitation mechanisms. It is also important to note when there is a little or no vibration for comparison. Then perceived vibration levels. If vibration levels are a concern, a high vibration, a basic measurement should be taken under steady conditions with regular reviews if no issue are detected. Then main line. The following should be considered as a part of the design process for the main line. For example, bend should be separated by at least 10 pipe diameters. Then as many bends as possible should be eliminated and supports added as close to the bends as possible. Then, like number 2, I missed basically, use the long radius bends rather than short radius or mitigated bends. Number 3, the pipe layout should contain adequate guides and line stops where applicable. 4, I said that as many bends as possible should be eliminated or minimized. Pipe support should be added at heavy masses such as valves. Span between supports should be carefully assessed to minimize the long unsupported lengths. Long sections vulnerable to large transit deflection should be avoided. Spring hanger should be avoided or their number should be minimized. A wear resistance or a compliant layer should be inserted between the pipe and pipe supports. So these are the areas what we consider normally at design stage of the main lines to avoid FIV, AIV related issues. The tubing wise, small tubing wise, the following should be considered as a part of the design process for the instrument tubing. For example, sufficient bends or pigtails are incorporated to allow the tubing to accommodate the main line movement. Ensure that all supports are effective. Any mass upon the tubing such as valves, gauges and instrument is well supported. The instrument tubing is designed to a suitable standard with appropriate component and correct assembly, avoiding mixing different fittings types basically. So this conclude our basically discussion of the session. We'll take the question answer session again and then we'll say bye bye. We know that in many areas like in the Far East, especially Malaysia and Indonesia, fasting time already crossed, but other areas we are waiting for the fasting break, iftar, right? So now question wise, let's go to question answer. Last 5-10 minutes and then we'll say bye bye.
Assalamu alaikum, sir.
Walaikum
Thank you
salam.
for giving me a chance. Sir, I want to know that either we can design such detectors or vibrators, such a detectors that can detect such vibrations in plants, because the piping line is very integrated in the plants, so it's quite difficult for us to uh, recognize the exact position where the such vibrations are occurring. So either
See,
we can design such a detector as we design earthquake detectors to detect such strong vibrations to avoid such disturbance in the plant.
See, what is being done? Many plants, refineries, petrochemical plants, or the gas plants are working, or fertilizer plants are working, and such kind of issues are always under control, kept under control. So, first of all, it is a part of basic process designing aspects. When we are making P&IDs, the velocities are kept under acceptable range, number one. Number two, we know that the excitation sources from where these issues comes, mostly the reciprocating equipment or pressure reduction stations or normal like compressor or pumps. So at design stage, in accordance with API 14E, like design criteria is there, or if you go to API 521, API 520, where PSV is an associated designing aspects are followed, then ASME 31.3, where supports and flexibility analysis comes. So if plants are designed as per those aspects, so the consideration about AIV, FIV is one of the study as a relief system study, hydraulic sizing studies, equipment sizing studies. So this is one of the study at the plant design stage. If it is done, then the probability of having the vibration related issues would be minimized. Now, second part, if plant is already working, designed, and you are new and you are not sure whether this aspect is taken care, then as the on P&IDs, the excitation sources, which are identified under EI guidelines, we also given in this presentation. If you identify those particular equipment and their downstream piping is checked with vibration, you will be able to know where the vibration issues may come. If vibration is within acceptable range of the or threshold limit of the measurement, like natural frequency below, let's say 1 hertz, 3 hertz, then it is acceptable. You don't need to be worrying. But this issue is an issue if you are facing some kind of high vibration and some piping system failed due to that, then you need to take corrective action. So as such, there's a proper phenomena, working steps, and it works to minimize this threat. And many plants are working without having this kind of problem. Okay, sir.
Thank you, sir, for this knowledgeable addition.
Thank you. Thank you. Next question.
Next question, please. Sir, next question is from Mr. Adil Nawaz Khan. We have allowed you to speak. Could you please ask your question? Adil Nawaz Khan. Sir, I guess Adil is not available. Could
The
you please?
question is, what are the effects of flow-induced vibration on the performance of heat exchangers? See, flow-induced vibration means there is a high velocity, high turbulence, right? And it will certainly affect the efficiency of the heat exchanger, right? Here, due to erosion corrosion. Number two, it may also damage the tube or tube sheet connection at some stage. So when any heat exchanger is having flow-induced vibration, it means that the heat exchanger is undersized. So this is a immediate reflection of that situation. But if why this problem will come? This problem will come if somewhere the capacity of the plant is increased from capacity A to, let's say, 100% to 120, 130%, and heat exchanger may not have that extra capacity in its design. In that scenario, you may have a flow-induced vibration issues.
So, sir, next question is from Mr. Mohid Irfan. We have allowed you to speak. Could you please ask a question?
So here the question is generally what frequency is used for AIV? AIV, FIV studies are done at design stage of the plant, and after plant is designed, built, and in operation, then it is a reactive or reverse cycle. If there is any vibration issue, then you try to carry out the AIV, FIV study if that vibration issue is caused by this factor. Like Siddharth Rai, the main line LOF is between 0.3 to 0.5 in FIV assessment. If 2-inch valve are directly connected to the weldolette, then two plane bracing is required or not. Okay, so here the main line LOF is between 0.3 and 0.5. which is within the acceptable range, right? If valve are directly connected to weldolette, then two plane bracing is required. See, this is the piping design, right? If isometric is in front of me, then I can comment, right? Because in general, 2-inch valve, how the valve is connected, if it's a part of the main system or is a branch connection. If it's a branch connection, then like a two plane bracing would be required, as in my view, but it has to be seen. Okay, sir. Okay, sir. Thank you very much for your questions and the interest. It was good gathering in the month of Ramadan, and we look forward to meeting you next webinar, which we will plan after the Eid al-Fitr holidays. Thank you very much, everyone, and my team for supporting me. Thank you.